Okay, yes, thank you. So it's actually the power of one clean qubit, which is the important part here. So this is joint work with David Lim at CQT in Singapore. And okay, so start with a little bit of introduction. So the one clean qubit model as a model of quantum computation was proposed by Neil and Laflamme already in 1998. And it was kind of used for doing quantum computation on NMRs. So there's this, I think, I don't know how famous it is, but in 2001, the number 15 was factored using something like Shor's algorithm in an NMR. So this stands for nuclear magnetic resonance. And these are used by chemists all the time. And so you can view it as a quantum system where the qubits are really bad, but the control is really good. So there were several papers about this. So here the one by Neil and Laflamme. And what is technically going on here? So this NMR actually contains a lot of molecules that are specifically designed as quantum storage, and you work with all of them simultaneously, and you can maybe separate 1 degree of freedom properly, and the rest of your storage is essentially noise. So the initial state of an abstract one clean qubit computation is the mixed state, where you have one qubit that starts in a coherent state, let's say 0, and then you have main storage is just the totally mixed state, and that's what you have, and that's all you have on storage. Now, it would seem that this isn't good for all that much. Okay, so I think it's popping up. So this is the clean qubit, and this is the stuff that you would think is really not good for anything. And on its own, it wouldn't be good for anything, because if your storage is just simply garbage, then nothing interesting can happen. There are no intermediate measurements. That means that you evolve this system by doing unitaries, and in the end, you do a measurement. This in particular to not allow you to create some kind of larger number of clean qubits after measure. Right? So one could say that these are bad qubits, but the control is good. We basically don't have any restrictions on how good unitaries are performed. Okay, so there's a lot of prior work on this. So yeah, so the illustrations are all done by my student, and sometimes I don't know, but here it's clearly a library of prior work. So there are several problems that can be surprisingly done quite well on the one clean qubit model: testing integrability, computing Schatten p-norms. Shor and Jordan have shown that estimating certain parameters of Jones polynomials is a complete problem for the one clean qubit model. There are others parameters about the Jones polynomials that are actually complete for BQP, and the one clean qubit model should be a proper subclass of BQP. At least that's what everybody conjectures. So this is something. It's a different problem.
Does it include BPP, or are there classical computations you cannot do in the quantum one clean qubit model?
I don't think it contains BPP. It's this, yeah, testing the quantum butterfly problem. So yes. So now there's this whole issue with showing what people have called quantum supremacy. That means you try to show that a quantum model that is maybe more realistic than the full EQP model can do things that are hard classically. These things don't necessarily have to be interesting, right? So, but it's interesting to see if they are tasks and not necessarily tasks that have any practical relevance that you can solve faster on a quantum computer or a near future quantum computer than on a classical computer. And such results exist for the one clean qubit model, which is clearly somewhat more realistic than the fully fledged quantum model. And so here is this paper by a bunch of Japanese authors, the power of quantum computing with few clean qubits. And here, this model is in the setting of circuit complexity, right? You have the qubits that start in this one clean qubit rest totally mixed, and then you apply an arbitrary circuit, and that's what you can compute here. So their result is that the one clean qubit model cannot be simulated with additive error 1 over exponential unless the polynomial hierarchy collapses. Now there's basically two problems with this kind of result. One is that the additive error has to be exponentially small. And it is really such that pretty much all the time you wouldn't observe anything specifically quantum about this computation. Because really this corresponds to events happening with exponentially small probability only. And the second thing is, of course, that we don't actually know that the polynomial hierarchy doesn't collapse.
This is efficiently simulated, that means by BPP or what?
By a randomized circuit, yes.
Okay.
Yeah, so efficient simulation would here mean that you get the same probability distribution as up to 1 over exponentially small probability as the quantum algorithm. And that's a hard problem, at least as long as the polynomial hierarchy is hard. Here it is spelled out again. So if we assume that the polynomial hierarchy does not collapse, then there are polynomial sized quantum circuits that operate with this one clean qubit restriction, and they have acceptance and rejection probabilities so that no classical circuit can have the same. Yeah.
So here you switched from sort of error in the overall distribution to error just in the one output bit in the two different formulations of the statement. Is that kind of obvious? I think in the second statement, you're talking just about acceptance rejection probabilities, which would be like sort of the predicting one output bit. Well, in the first statement, you were, at least your explanation of that, you were talking about sampling from the distribution with small variation.
You can achieve this one, but yeah, yeah, I agree. It's a slightly different formulation. So then there's another result which says that you cannot efficiently approximate the output probability distribution again with its most exponentially small error unless PQP is in BPP. So all these hardness results, and there are others, they have exponentially small error and they rely on some complexity assumptions. Now, we would like to do without these two assumptions. And where can we show separations between different complexity parameters? Well, we can do so in communication complexity, right? So our goal is to show hardness of classically simulating a communication model with the one clean qubit restriction and not using any unproven assumptions. And we would hope for having hardness results for error that is maybe 1 over poly n or maybe even larger than that, because that's stuff you could observe actually. And what I have in mind here is really, you could try to implement such a setting by having your NMR, which basically wants this one clean qubit system. And then you have the different players, let's say Alice and Bob in communication complexity. Alice has an input, Bob has an input, these classical inputs that we have. And then Alice goes to the NMR, fiddles with it, and then leaves. And then Bob goes to the NMR, fiddles with it, and then you do the measurement, you get some result. And essentially, you would have to argue that the NMR has some bounded storage capacity. So that this being the communication medium. Okay. We also look at the situation where the simulation error is constant, but we don't have definite results for that. Okay. So communication complexity. The standard model is 2 players. You will also have a 3-player model. So there are Alice and Bob, inputs X and Y, to which they have some kind of oracle access. Right? So they are stored in read-only memory, so they cannot abuse these inputs as some kind of additional storage. Okay, this is actually the standard model without these memory restrictions first. So they want to compute f of x, they interact possibly, or maybe they interact not, just a one-way protocol from Alice to Bob maybe. And then in the end, they compute the function value. And there are different models of this, depending on how you communicate, if you allow error or not. So for instance, there's a quantum communication model, which can have or not have shared entanglement between Alice and Bob. There's a randomized model, which can or cannot have public coin randomness that can be accessed without communication. Right? And you can allow epsilon error or even worse than that. So let's try to instantiate the K clean qubit model and then the 1 clean qubit model for this. So Alice and Bob, they have workspace. Yeah.
So the communication is bits and not qubits?
Here the communication will be qubit. But there are classical models of this and communication bits, right? So if we have K clean qubits, then there's this state where we have K coherent qubits, and then there's some M that start out in the totally mixed state. And this is all that the players have to communicate. They have no additional private workspace, and they have to use these qubits for communication. And so the qubits in the world. And they are somehow distributed in the beginning among the players, right? So let's say Alice starts the communication, then it makes sense that she has at least one of the clean qubits, otherwise her first round would be totally wasted. But otherwise, Bob could have some, Alice could have some, if there are more than one. There's no prior entanglement here, because that would again be usable to create coherent states. Like let's say you have an EPR pair that is shared, then Bob can communicate his part of the EPR pair to Alice. Alice can undo that EPR pair and gets 2 clean qubits for free. So we cannot allow prior entanglement here. There are also no intermediate measurements in all of this. So we allow an arbitrary projective measurement at the end of the computation. And then the 1 clean qubit model is just where K is equal to 1. And in communication complexity, we like to have a complexity measure for studying what is the complexity of a function. So we have this measure Q1 of f, which seems to us to be the appropriate definition. So I will define more details about this stuff in a few slides. So there's an additional issue with protocols having to be clocked or not clocked. And I'll explain that later. So the most general is that the protocol is clocked. And then we have a function we want to compute. And we assume that there's some bias that the protocol produces in its output. So 0 inputs are accepted with probability 1/2 minus epsilon at most. And 1 inputs are accepted with probability 1/2 plus epsilon at least. So this gives us some leeway. And then there's amount C of communication that takes place. Right, it's the standard rules. You send the qubits back and forth. And then we say the cost of this protocol is C over epsilon squared. And this I will have to justify. I mean, C is obvious, right? The communication is C, so the cost should reflect that. But here, this epsilon may be rather small. I mean, if epsilon is a constant, then this seems to be petty, but epsilon can be potentially very small. And so we don't denote the complexity of the function as the infimum over all protocols. That implies also the epsilon here, right, of this cost C over epsilon squared. So why did we define it like this? It is well known that in typical modes of communication complexity that have error, like quantum communication complexity or randomized communication complexity, you can amplify success probability by repeating and making a majority vote. Yeah, and then you can go from constant to any epsilon by a factor log 1 over epsilon. But if this gap is 1/2 plus epsilon against 1/2 minus epsilon, then it actually takes such a factor of 1 over epsilon square as we have here. Now, it seems unlikely. Yeah?
Classically, it takes epsilon squared. With quantum, you can do amplitude amplification and get by with 1 over epsilon.
Yes.
It doesn't really use a lot more extra qubits.
Well, log n is already plenty. So this actually is an open problem. Can we, how well can we amplify? And I don't know anything better than this 1 over epsilon squared. At least not with 1 qubit or anything like that. So we simply allow protocols to have an arbitrarily bad bias, but then punish the protocol in the cost for having bad bias. And using just repetition, it cannot actually be done in the model, right? Because you would have to store how many, you would have to count how many successes or how many acceptances, how many rejections. And you can't really do that. But let's say, okay, you can take your protocol and then you just factor in the cost that would need in the number of repetitions to just classically get a good result, a good enough error bound. So now, what are these clocked and unclocked models? Basically, the clocked model works like this. You have your clean qubit, you have your mixed qubits, and then Alice applies a unitary, there are some communication takes place, Bob applies a unitary, some communication takes place, and so on and so on. And if you do this, then you can maybe assume that you can use a particular unitary in round 1, another unitary in round 2, another unitary in round R. So not only are these unitaries indexed by the input, but they're also indexed by which round Alice or Bob are in. And so it is as if there is an additional clock that is visible to the players. Yeah.
Must Alice know which qubit is clean?
Yes, they know which is the clean qubit.
Is it necessary?
I haven't seen anything being done without the assumption that you know which one is the clean qubit. So then it might be difficult to find it, right? In particular, without measuring. Okay, you have a unitary that depends on I and also on X or Y. And this is some notion of a ghosted communication channel. That means in every round you can communicate a different set of qubits. It's predetermined which one, but you can have any choice. So this is the most, yeah.
Earlier you said that only the clean qubits would be used for communications. In this case, it seems that
No. That is not the case. You can communicate any subset of these qubits, not just the clean one. Yeah.
So the pictures suggest that Bob cannot do controlled operations on the qubit.
Why not?
Well, because the V1 doesn't look like it.
Yeah, I mean, it would be difficult to make a drawing. So once you have applied this unitary, there's not necessarily any clean qubit anymore, right? It's, something happens to it and you know maybe where it went, but for instance, this could be just shifted to this or this, and then Bob could access it. So,
sorry, another question. So, sort of the partition in who holds the, like Alice holds these qubits and Bob holds these qubits, does that shift over time?
yes.
Okay, so, because your picture suggests that it's always sort of the top qubits that belong to the U player and the bottom qubits that belong to the V player.
But the U's allow for permutations of the qubits.
Yes.
Yeah, but they only act on the upper half of the qubits, right? The picture is maybe slightly different from the actual model.
In the picture, initially, these qubits belong to Bob and these belong to Alice. But then some of the qubits that belonged to Alice now also belong to Bob after this. This is this wire, for instance. Initially belongs to Alice, but then in the next one belongs to Bob. All sorts of things can go on there.
I guess you could think of that there's just one computer and they take turns operating it. And then if you want to turn it into communication, then you kind of have to figure out which qubits need to be sent.
Did you also count the M in your model for the cost, or do you only count the number of alternations?
We count how many qubits are that are essentially here pictured as this one wire. How many qubits are communicated in total?
So we don't care about M basically in this picture.
What is
Like on the left, it's the number of qubits.
No, we actually don't care about that. So you have arbitrary many of these. But I can think of use of having many more than communication. So then there's the semi-unclocked model in which, well, basically they have to use the same unitary in, okay, this is maybe also adding some confusion because now the unitaries are drawn as to go over all of the qubits. Of course, there's always such a unitary, namely Alice applies a unitary to her, and that is tensored with an identity on the qubits that belong to Bob and so on. But in every round, it has to be the same unitary, one for Alice, one for Bob, depending on X and Y, but not on the particular round. However, at some point, somebody has to say, this is the end, right? So that's why I call this semi-unclocked, because there's a time bound. So they say after R rounds, I'll stop. but you cannot really use this information. And actually, the difference between these models is not that large, as we shall see. So this protocol stops after a fixed number of rounds. And we also assume that the communication channel is fixed here. So this is the most restricted of these models. Okay, so now let's compare these models first a little bit. So we are given a Klauck K clean qubit protocol with communication C and a bias of epsilon. Then which is the same picture as before, we can construct a one clean qubit protocol. Again, instead of K has only one. And this is a typeset a little bit unfortunate. So the communication is C plus one, and the bias now goes down from epsilon to epsilon divided by 2 to the K. And this is actually a very simple construction. So we start with one clean qubit and the rest are now. So here we have M plus K qubits. Here we have M plus K qubits in the totally mixed state and one qubit in the pure state. Then we do something in the first step and tell you what in a moment. And then we just simulate the previous protocol in the same way as before and then measure. So what is A? Well, it's kind of obvious what to do. You apply this unitary that flags the first qubit here if the other qubits are in the state 0, which happens with probability 2 to the minus K. And it doesn't flag otherwise, and you extend this to a unitary. Then you run now the protocol as if you had these K clean qubits and just do it exactly the same unitary as before. And you do a measurement, a combined measurement on all the qubits, where essentially the idea is to check if the first qubit is 0. If that is the case, then you were unsuccessful in obtaining more clean qubits and you toss a coin. And otherwise, you do the measurement as per the previous protocol. And this, you can easily see, gives you a bias of epsilon divided by 2 to the K. Right? So this is the. Now.
That had nothing to do with communication, right? The same story applies to the usual circuit
Yes.
version of the one qubit.
Okay, so we are done with a Klauck qubit with K clean qubits, communication C bias epsilon, ghosted channel, arbitrary projective measurement. So this is general, and we get a semi-unclocked one clean qubit protocol with communication C times log C, and the bias epsilon divided by 2 to the K, a fixed communication channel, and you measure only one qubit in the end. So you see actually the gap between this clocked and unclocked model or semi-unclocked model is not that large, at most a log factor. And of course, if you go from K to 1, you expect this bias to drop by 2 to the K. Okay, so we start with this clocked and everything nice. We go with theorem 1, I guess, to the one clean qubit model. That is the thing we already did. Then we change this into measuring only one qubit, which is relatively easy and still ghosted channel. And then we turn this into a trace estimation protocol. And you take this Oh, this is only about the measurement. So you basically take this arbitrary projective measurement and find a suitable unitary so that in the end you get to measure only one of the qubits. That's then the one that you use. From there, you can fix the communication channel with some modifications of some permuting qubits and then always sending the same qubits around. And then you can turn this into a trace estimation protocol, which you can do with all one clean qubit computations with a technique that is from the paper by Shaw and Jordan, who basically showed among these things with the Jones polynomials that the problem of trace estimation of a given unitary is complete for this kind of model. Now, what happens here when we do this is that the acceptance probability depends only of the trace of a given unitary operator. And that's going to be important. Now, we have everything, but we're still in the clocked model. And we wanted to go to the unclocked or semi-unclocked model. And for this, we add another log R, where R is the number of rounds, mixed qubits. Mixed qubits, we have enough, right? And these qubits, we think of them as starting in a random standard basis state with probability 1 over R. And then basically in every round, you add 1 to this counter. This is a unitary that is independent of the round. Add 1 to the counter. So then you use these basically to control which of the original clocked unitaries you are going to apply. Now, what's the problem here? Well, this counter, it starts somewhere between 1 and R. Right? It doesn't start with a 1. Well, it could, but only with probability 1 over R. So it starts with some number k between 1 and R, and then in every round you add 1 to it modulo R, which is a round independent. You use these qubits to control which of the unitaries from the clock model you're going to apply. And but basically you get a more protocol like this. And this hides that you're basically controlling using the I over R mixed state, which of the previous unitaries you are applying. So you can think of this as starting with a number k from 1 to I, and then applying the unitaries of the original protocol, k, k plus 1, k plus 2, k plus 3, R, 0, 1, up to k minus 1. And why is that? So we have used this step that I didn't explain from the paper by Shaw and Jordan, that we replaced a given protocol that defines a unitary and put it into the trace estimation circuit from Shaw and Jordan. And we have these counter qubits. Now, acceptance probability depends only on the trace of the product of these unitaries that we have, because we're applying one after the other, Alice and Bob, Alice and Bob, Alice and Bob. But we're starting somewhere in the middle and then go to the end, go to the beginning, and then end up back in the middle. But the trace has this cyclic property where if you shift the unitaries that you want to know the trace of, the trace doesn't change, right? The trace of A, B, C is the same as a trace of C, A, B is the same as the trace of B, C, A. So you can, so it doesn't matter in which order you apply the unitaries because of the cyclic properties and because we have turned this protocol into trace estimation. Okay, so this is about the model. And I always liked one-way communication complexity, which is a simpler model, and this works here as follows. We have our one-king qubit, our mixed state. Alice owns some of the qubits, applies a unitary, then sends some of the qubits to Bob, who then applies a unitary, then there's a measurement, and I guess ideally the measurement should really be only on the qubits that are belonging to Bob now. So if Alice retains any, which doesn't really make any sense, because if she doesn't use the qubit, why have it to begin with? So Alice applies a unitary, sends the qubits that are used to Bob. Bob applies a unitary on all the qubits in his possession now, and then there's a measurement. And we get this characterization, which is kind of terrible. So there's a mode of communication complexity called PP protocols, which I'll define in a moment. So we have this measure one-way Q1 of F defined exactly as before, only that this restricted protocol with one message being sent only. And this is sandwiched between 2 to the PP and 2 to the PP up to some poly n factor. Now, notice that this is typically much larger than n, the input legs. In fact, there's a gap of poly n between these two bonds. So in the one-way setting, essentially, this model kind of falls apart. You cannot do much useful. Okay, so there's an upper bound. We're simulating these PP protocols, and here's the definition of what a PP protocol is. It's called the weakly unbounded error protocol, and you have a function is computed correctly with probability larger than 1/2. Let's say 1/2 plus epsilon. And if your error is then 1/2 minus epsilon, then the communication, and the communication is C, then the complexity is C plus log 1 over epsilon. And well, this is sort of defined by Frankel-Simon in 86 as a communication complexity analog of the classical complexity class PP, which is can be defined similar to this also, but is really usually understood as majority non-determinism. You have a non-deterministic machine, and you require the calculation to be correct with probability larger than 1/2. And there's another communication complexity class where the error is also support the success probability or correctness probability has to be larger than 1/2, but you don't punish the protocol for having a small bias, and that is called UPP. It's a much more powerful class. So the lower bound comes from margin complexity of sign matrices. And essentially, what we get is the best possible bias at most this parameter that I'm going to define. So the margin of F.
So in PP, you define the cost with a log 1 over epsilon, right?
Yes.
So that is a very different way of defining the cost, right? Because in the other you have the epsilon.
It is very different indeed, but it comes from a completely different motivation, namely some kind of this kind of majority non-determinism. And yeah, it's something that's been around for a while, and yeah, you do not try to amplify PP protocols to constant error, basically. Whereas that's the natural thing to do with this one-king qubit protocols. Okay, so there's a general result that PP protocols can be assumed to be one-way. And essentially, if you want to make things simple, let's say you have a protocol that has a bias of at least 2 to the minus pp and the communication of at most pp, then this c plus log 1 over epsilon is something like 2 times pp still. So you want to turn this into a protocol that has communication c and a bias epsilon divided by 2 to the c, and the cost 2 to the 2 pp and or c times 2 to the 2 pp in the one clean. So we want such a one clean qubit protocol, and the way to do this is essentially to again take c mixed qubits, do this unitary that flags a qubit, a clean qubit, if this contain the actual classical message of length c, which happens with probability 2 to the minus c, right? It's the same as in this theorem 1. And then you can do this with one clean qubit. So it's kind of a trivial construction, but that's basically all you can do. Now, what is the margin of a function on x times y to, let's say now -1 and +1? This comes from computational learning theory, and the margin is the supremum over the minimum of x and y, and of the absolute value, this is missing here on the right, of the inner product between ux and uy, where ux and uy kind of sign represent f of xy, namely these would be unit vectors and ux and yy, vy, and then the inner product between ux and vy has to have the same sign as f of x comma y, which you can say that's the product of this inner product, and the function value must be at least larger than 0. Right? Then you can say that these vectors sign represent a function, and you try to drive this value as high as possible by choosing sufficiently good unit vectors. And this is basically the margin that you get achieved, and it's achieved, has to be achieved on all inputs. So this is very useful in learning theory. And basically in communication complexity, this 2 to the pp is roughly 1 over the margin up to a factor that is essentially log n, not even wholly, just order of log n. And for some other measures that are well known, margin complexity is pretty much the discrepancy, and the discrepancy, whatever that is pretty much 1 over the gamma to infinity norm of the associated communication matrix. So, and what we show is essentially, well, our poor one-way protocol needs to be at least m to the -2. This is this epsilon square. So the margin is essentially the best bias you can get. And again, if you massage this such a protocol a little bit, you get that you measure only 1 qubit, and this is your acceptance probability. You have the identity on Alice's qubit tensored with Bob's unitary, and this goes times the unitary of Alice tensored with the identity on Bob's. And this goes divided by 2 to the m plus 1. M was the number of mixed qubits, and this is the bias you get. Now you can define this to be the x operation ax, and this to be the y operation by, this depends on y and this depends on x, but not vice versa. And then this bias here, you can see that it is, well, it's this. Then this is the trace of by times ax, still divided by 2 to the n plus 1. But then this trace of a product of two matrices is just the inner product between the matrices viewed as vectors. Right? So if you view by as a vector and then ax as a vector, then this is the no need for the transpose here actually, right? Because we use this notation. And then what is the length of these vectors in the 2 norm? It's 2 to the m over 2. And we have this additional 2 here, and then this is the inner product between these two vectors, and then this can be normed by dividing. Well, these are automatically normed if you divide them by 2 norm. So what turns out, if your protocol has bias epsilon, then m of f is at least epsilon over 2. And so this is the best epsilon you can get in this one-way fashion. And then this 1 over epsilon square is a lower bound for the best epsilon you can achieve, and the margin just bounds that best epsilon. So this is at least 4 over m squared, and this 1 over m is at least 2 to the pp minus log n. So these protocols can be fairly bad. Now let's try to see if there's something we can do with protocols. And here we define what is an epsilon simulation of a quantum protocol. And implicitly what we mean is a quantum protocol that has this storage with one clean qubit and the other qubits not being clean. So you have a quantum protocol, and there's a function that's associated with it, and for all inputs x, let's say it accepts one input with probability alpha and accepts 0 probability with probability beta, and beta should be smaller than alpha. Otherwise, it's not a hard task. And an epsilon simulation of such a quantum protocol is a classical protocol, so that one inputs are accepted with probability a little bit less than alpha, but not worse than alpha minus epsilon. So epsilon is the additive error here of the simulation, and 0 inputs with probability beta plus epsilon at most. And then there should still be a gap between the two numbers, otherwise it's easy to do. And okay, so the thing we can do and fully prove is simulation with 1 over poly and additive error. And so the statement of this theorem is there is a function 0, 1 to n, 0, 1 to n, and there's a one clean qubit protocol with communication log n, and its acceptance probability is not going to be close to 1 or larger than half. It's actually going to be a pretty small number, but still associated to this function. And simulating this protocol with 1 over n to the 4th additive error requires theta of n communication. So the quantum protocol with one clean qubit uses log n communication, actually over 2 rounds. And any protocol that has the same acceptance behavior and has an additive error of 1 over n to the 4 must have linear communication, so exponentially more. So that achieves those two goals, basically, that the hardness is fully proved, and the error is 1 over poly, the simulation error. So what's the function? Call it middle of x, y, and it is 0 if yeah. So yeah, okay. So 0, 1 inputs. It is 0 if the sum of xi, yi is equal to n over 2, and it is 1 if the sum of xi, yi is not equal to n over 2. So how can I do that? So first I describe a standard quantum protocol. There's no qubit restriction here. So Alice prepares this state is a superposition of the i's and the xi's. Bob creates puts the product of xi, yi into a phase factor that is easy to do for him. And he leaves the xi where it is, right? And sends this stuff back to Alice. Then Alice erases this xi, so she ends up with, which she can do because it's her input, you can have an oracle access to that. And then basically we have the state -1 to the xi, yi, I, and we do a Hadamard transform and a complete measurement in the computational basis. Then it is fairly, well, the protocol outputs one of them measures the all 0 string and outputs 0 otherwise. It's fairly standard stuff. Then it's not hard to see that, well, we communicate 2 log n plus 2 bits. Using log n plus 1 clean qubits, we reject the 0 inputs with certainty and accept 1 for inputs with probability 4 over n squared.
When you say apply Hadamard transform on what? Like you have a register that has n values there?
Again, this is a standard quantum
No,
protocol.
like behind this, like if you go back a bit. So or is the little n is like 2 is a power of 2?
You can assume that it's a power of 2.
This is like a distributed version of Deutsch Joseph.
Yes. Okay, so you have a gap. 0 inputs are rejected with certainty, 1 input accepted with some small but sizable probability. So this is a gap of 4 over n squared. However, we're still using log n qubits, which is has nothing to do with the 1 clean qubit model. However, we can use our old trick and take a hit in the bias by 2 to the log n plus 1. And now we still reject 0 inputs with certainty and accept 1 inputs now with probability at least 2 to the n over 3. And now the question is, what can a randomized protocol do that has additive error 1 over n to the 4th? And this still leaves a sizable gap of n to the -3, basically, between acceptance and rejectance. And I'm not going to say much about the lower bound. It's a big appeal to Rosborov's distributional complexity of disjointness paper. And this uses the rectangle bound to give a lower bound for disjointness, but it can be used for many other functions as well. And basically, you can also think of there being a reduction from this problem to disjointness, or rather the other way around. And the thing is that the rectangle bound is not sensitive to acceptance probabilities being very small. You can actually technically write it as a linear program, and the error is not some epsilon, but let's say 1 over n to the 3, and then you can still get this bound through and get the linear lower bound proof. Now, okay, I have a lot more material, but okay, so what about constant error? So here's a conjecture that I really like to prove. We have a function f, a constant epsilon, and a one-clean qubit protocol that computes f exactly without even any error with communication log n, and every classical simulation with epsilon additive error requires omega of root n communication. So this is the problem. I call it the ABC problem, and it's in a three-party communication model, which is number in hand. Every player sees his input or her input, and 3 players, and the quantum protocol at least is one way. So Alice or Charlie, what Alice gets is a matrix from the special orthogonal group. So it's an orthogonal matrix, and it also has determinant 1. Bob gets another matrix, and Charlie gets another matrix. And then there's a promise. Namely, the product A times B times C is either minus the identity or is plus the identity. And you have to decide which. Promise is it is either. You have to decide which. Okay, so that is the problem. And here's this kind of trace estimation circuit that pretty immediately springs to mind. So you have one clean qubit here, and here you could actually put any state there, any mixed state. This actually works as a catalyst, basically. So you put the Hadamard transform on this clean qubit that's been done by Alice. Then Alice uses this qubit to control application of A on the remaining log n qubits. She can do that. Then she sends those log n plus 1 qubits over to Bob. Bob then uses the clean qubit. Isn't really clean anymore, but it's still the same qubit, to control application of B. Sends the log n plus 1 qubits over to Charlie, who controls and applies C. And then Charlie can Hadamard the first qubit and measure the first qubit. Now, what happens? If A, B, C is the identity, then basically these 3 control operations cancel each other out. It is as if they would never have happened. Then the Hadamards cancel each other out, and what you have at the end here is just the 0 state. You measure this one, you see 0, and then you know ABC was equal to I, and you output 1. If, on the other hand, ABC is minus I, then a phase factor appears, and you can basically treat it as if it appears on this qubit. So you get the phase factor here, and if you then apply the Hadamard, you get the measure. You measure 1, and then it. Okay. What you have here is 0 plus 1 divided by square root of 2, and what you get here is then 0 minus 1 divided by square root of 2, and that's maps back to 1. So this protocol doesn't have any error, has communication about 3 log n, and definitely you also get this state back in the end. So I don't have that much time. So there's a protocol, a randomized protocol that does this ABC problem with communication square root n and let me just try to sketch the protocol. So if ABC is identity, then if you take the ith row of A multiplied with B and then C's column, the ith column of C, then you get a 1 for every I. On the other hand, if this is minus I, then you get a minus 1. So you can just simply choose any I could be just 1, for instance, and or go to a somewhat different problem that I call the little ABC problem, where you have 2 vectors from the sphere and an orthogonal matrix, and you get the promise that its inner product is either 1 or minus 1, and you want to decide that. And we have a protocol for that, and the protocol has 2 phases. So Charlie and Bob have a lot of shared public coin. These are just random vectors from the sphere, chosen independent of the input. And if you have enough of them, namely 2 to the root n would be enough, then you can find one of those vectors, W, that has an inner product at least n to the minus 1/4, n to the minus 1/4, with this vector in the public coin, and you can, and Charlie can tell Bob which vector to use, which takes square root n bits. And then Bob just uses this W instead of the actual C, and then Alice and Bob can run a standard known protocol for approximating inner products with an error n to the minus 1/4, right? This was n to the minus 1/4. You make it a little bit smaller than that. And if you plug all these things in, then this second step also costs square root n. And I skip the analysis, which is pretty easy. And so skip this. And okay, I'm basically just going to describe a geometric conjecture that would imply a square root n lower bound for the same problem, which is probably hard. I won't have time to give this lower bound for this little ABC problem. We have an n to the 1/3 lower bound for that, but we have no lower bound for the big ABC problem. Now, the little ABC upper bound gives an upper bound for the big ABC, and a lower bound for big ABC gives a lower bound for little ABC, but not the other way around. So I'm just basically going to flash this conjecture, which is about the special orthogonal group. And I call this geometric extractor, product extractor type statement. So let's say you have M and R subsets of the special orthogonal group, and there's a uniform distribution on this set, and let's say that M and R are moderately large, right? They have some randomness in them, but it's not a very big amount. Now what we do is we have these sets from a product, and we can take a matrix from M and a matrix from R, chosen randomly from these sets M and R, and multiply these 2 matrices. And the claim is that if you take the density function of the probability distribution that arises when you form this product, right? Take B from M independently, you take C from R, you multiply the 2, and that gives you a probability distribution again on the special orthogonal group. And the conjecture is that most inputs have a density that is constant, which is another way of saying up to an exponentially small subset of the orthogonal group, this distribution is close to uniform, right? So you take 2 moderately random subsets and you form the matrix product of two random elements, you get something that is very close to uniform. That's the conjecture. Unfortunately, I cannot prove this. You get the lower bound from this conjecture relatively easy. And so let me also just flash what we have for the little ABC problem. If Bob and Charlie can talk arbitrarily, but Charlie sends only little o of n to the 2/3 bit and Bob only little o of n to the 1/3, and then they send the whole conversation to Alice, who decides, then you have a large constant error, which means you need either Charlie send more than n to the 2/3 or Bob send more than n to the 1/3. And this is a trade-off that you can achieve in the protocol that I sketched a couple of minutes ago. You can make the first stage where you choose this vector with a large overlap. You can make this one more expensive, and then the overlap is better, and then the inner product can run with less precision. And we show that at least in this trade-off, we get a tight lower bound. Ambitious here. Yeah, and the ingredient there is this so-called equator sampling. It's a generalization of Klauck and Regev that I won't explain in detail, but you have what Klauck and Regev have is you have a subset of the sphere of a certain measure. You hit it with a random hyperplane and you look how large is that induced subset on the sphere inside that random hyperplane. And it's a result that gives a concentration of measure, namely deviations by mod t go exponentially large in t. And our generalizations go from sets and their size to distributions and their density functions. Okay, so it's done. Open problems. Well, the big open problem is to get this lower bound for the ABC problem conjecture to be 0. And also this constant additive error is the same as just looking at the communication complexity, because that's then same as constant error approximation. Any n to the delta would be fine. A specific lower bound method for this Q1 of f would be nice. For instance, we know that disjointness has to be at least square root n because the quantum complexity is anyway already root n. And we can do disjointness in this model with order n, communication for cost. And yeah, something specific that, for instance, rules out that you can do Grover-like speedups. So my conjecture would be that probably you cannot do better than n, because anything. Or Alice gets a set, a subset of 1 up to n. Bob gets a subset from 1 up to n. And they want to know if the sets intersect or not. No, just whether they intersect at all. I mean, you can also consider computing the size of the intersection, but that's actually harder. Okay, another maybe somewhat intriguing question is whether we need more than linear communication for this type of protocol for some functions. So we know in the one-way Alice to Bob setting that is the case. And I would be surprised if you could do a random function with linear communication. Okay, that's all.